So we're going to get a look here at the calculation, the actual calculation of the standard deviation of a data set, a small data set, because as you'll see going through this can get a little bit expansive, and it's not the most horrible thing in the world, but it is definitely more involved than any other calculation that we have done or quite frankly really will do in this semester. So, first of all, this data set is from the PowerPoint slideshow. We already used it in the example for deviation, so I set up the table already with the data values and the deviations filled in as from the PowerPoint already. Save us a little time. If this was a new data set, we'd have to do that on our own. So the first step is to calculate the mean, and then to go through and calculate the deviation of each data value. You can imagine with a data set of, say, 100 values, we could be here for a while doing this. So it's an involved calculation if you're doing it by hand. We typically won't be. There will be a future video where I show you how to do these by hand, or sorry, by technology, but for the moment we're just going to take a look at the process here. So, the standard deviation formula, we looked at it in a previous video, and we walked through all the steps of it, one at a time. Now, the first step was to calculate the deviations. Done. The next step was to square each deviation. So I'm going to add another column to this table where I'm going to take each deviation and square it. Now, what we'll see here is that the values that are closest to the mean will have the smallest square deviation, and the values that are furthest from the mean will have the largest square deviations. And values that are approximately or the same distance from the mean will have approximately the same square deviation, or values that are exactly the same distance from the mean will have exactly the same square deviation. So let's just go through it then. Negative 10 squared is 100. Negative 4 squared is 16. So we can see the greater distance and therefore the greater influence is maintained. Whereas this 17 here has the least distance and therefore the least influence on the mean. 22 is 4 spaces above the mean, which is perfectly balanced by this 14 being 4 spaces below the mean. But the idea is that the influence they have, regardless of which side it is towards, the influence is the same. And lastly, we square the deviation of 11. So, we're going to use calculator here, definitely. The bigger this gets, the uglier the numbers can be, certainly. We're lucky here, and again, I designed this data set to have a whole number for the mean, just to give us some friendlier deviations and therefore some other friendlier numbers to work with. If the mean had been a decimal, which is, quite frankly, what typically happens, then the deviations can get ugly. The square deviations get even uglier. So I chose some nice values here to give us a good thing to work with, something that's relatively simple. So, start with the deviations, square them, add them up. This is where the calculator is going to come into play. We add all of this up. We should get from it 254. Now, at this point, we're done with the table. We're going to return to this formula because what we now have is the value for the numerator of this fraction. Now, the sample size. Well, fortunately, it's a small enough sample. There are 5 data values in it. Now, again, you're just going to have to trust as to that -1 that it is necessary for it to be there for now. It has to do with a topic called degrees of freedom, which is certainly way more important to the people who developed all of these formulas than it is to the people who are using them. So for us, it's just a matter of, it's there, we have to use it. So we end up dividing 254 by 4. Which gives us 63.5. Now we're not done yet. The first thing that we should notice here is, again, that the standard deviation is supposed to be sort of like the average distance from the mean. 63.5 is far too large of an average distance from the mean. Far too large. I mean, look at these. The furthest one from the mean is 11 spaces away. You can't have an average that's bigger than any of the numbers that's there. So that doesn't really make much sense. So the square root is an easy thing to forget, but it is a very, very important part of this. So we now turn to a calculator and do the square root of 63.5. And what we get is 7.968, etc. Now, we don't need to go hog wild with listing decimal places. We will follow the rounding rule, and that is that since the data values are measured as whole numbers with no decimal places, we can round this to 1 decimal place. Now, if we round it to 1 decimal place, the 6 here tells us to round up. So we're already at 7 9/10. If we go up to 7 10/10, that actually becomes 8. Well, excuse me, not equals, approximately. So what this is telling us is that the average distance from the mean is about 8 spaces. Now, intuitively, well, maybe that's a bad word to use. I don't know how intuitive standard deviation really is. I mean, it certainly doesn't seem like we should be an average of 8 spaces away. But for now, we trust the formula, and coming up later in the lesson is how we actually use this to interpret what's going on. See, I say it's, for all intents and purposes, it's the average distance. The standard deviation is never really intended to be interpreted all by itself. It's meant to work in conjunction with the mean. So that will come up very soon, and we'll see exactly how this figures into the mean and how the data set is spread out from the mean.